The textbook on your shelf says gravity curves space. That sentence has been printed in every physics classroom for a century, and the sentence is wrong. Not completely wrong. The math works. But two rival descriptions of reality, one built on twisting, one built on stretching, match every single experiment ever performed. Nobody can tell which description is correct, and the physicist who started the whole story rejected the version the world adopted. Here is what the official record says. Mass warps the fabric of space and time. Objects follow the curves. Every observation, from bending starlight to gravitational waves, confirms the prediction. On paper, the case looks closed. But the case file has problems. In 1928, the physicist who built the framework began exploring a rival version, convinced that flat spacetime with torsion could unify two branches of physics. The creator tried to replace the creation. Decades later, other physicists revived both abandoned frameworks and proved those frameworks match every prediction. Three geometric languages describing one reality, and no experiment ever built can tell them apart. That should bother you. The equivalence principle holds to 1 part in 10 trillion, and all three descriptions honor the principle equally. Nobody knows which map is the real one. So the question is not which equation is correct. The question is whether the feeling of weight beneath your feet, the most constant sensation you have ever known, has ever been explained at all. If you enjoy journeys that change how you see reality, hit that like button and subscribe. Weight is a liar. That sentence sounds dramatic, but the evidence behind the sentence is worse than the drama, because right now, at this very second, a pressure is pushing you into your chair, pressing your feet into the floor, pressing every organ in your body downward. You have felt that pressure every single day since birth. And I'm about to show you that nobody, not a single physicist on Earth, can explain what that pressure actually is. Start with a deceptively simple question. What does a human body actually report during freefall? Forget the panic and the rushing air. Strip away the psychology, strip away the air resistance, and ask what the body itself reports during freefall. The answer is nothing. Absolute zero sensation. A person stepping off a tall building enters a state within seconds that the human nervous system cannot distinguish from floating in deep space. The inner ear goes quiet. Organs stop pressing against each other. Muscles that spend every waking moment fighting the downward pull suddenly have nothing to fight. Every biological sensor in the human body, every nerve ending calibrated over millions of years to detect gravity, falls silent the instant a person stops resisting. That silence is total. Drop a thermometer during the fall, and the thermometer floats beside you, weightless. Release a glass of water, and the water hangs in midair, a trembling sphere. Nothing inside that bubble of freefall, no instrument, no sensor, no nerve, can tell you whether you are plummeting toward concrete or drifting through interstellar void. The physics of the two situations, the measurable physics, the physics that instruments can record, is identical. A man sitting in a patent office in Bern, Switzerland, in 1907 realized the full weight of that silence. His name was Albert Einstein, and he was not yet famous. He was a clerk, a government employee reviewing technical applications during business hours, stealing whatever time remained to think about physics. Einstein had published the special theory of relativity 2 years earlier, but the theory said nothing about gravity, and the gap bothered him. On one particular afternoon, while writing a review article for a journal called the Jahrbuch der Radioaktivität und Elektronik, Einstein imagined a person falling from a roof. Not a dramatic plunge, but a quiet thought experiment inside a quiet office. And that mental picture produced what Einstein later called the happiest thought of his life. The falling person feels nothing. No pull, no tug, absolutely zero force acting on the body. If an observer dropped a ball during the fall, the ball would hover beside the observer, motionless relative to the observer's body, exactly as a ball would hover beside an astronaut floating in empty space. Einstein grasped the implication immediately. A falling person and a floating person are physically identical. Both bodies report the same data. Every instrument gives the same reading, and no measurement devised by any physicist in history, can tell the two situations apart. Years later, in 1919, a New York Times correspondent visited Einstein's home in Berlin. Einstein told the reporter a colorful version of the story. A man fell from a neighboring roof, landed on a pile of garbage, and survived nearly without injury. The man told Einstein that during the fall, the man experienced no sensation commonly considered the effect of gravity. The reporter published the tale as fact. Einstein, apparently, was amusing himself. The correspondent never realized the physicist was playing a prank, dressing an abstract insight in the costume of a slapstick accident. One of the most important ideas in physics, as a result, entered the historical record tainted by a joke. But the insight behind the joke was lethal. If a person in free fall cannot detect any force acting on the person's body, if every measurement device the person carries reads 0, then maybe the force does not exist. Maybe what we call gravity is not a force pulling objects downward. Maybe what we call gravity is a different phenomenon entirely, one that only looks like a force when you stand on solid ground, when the ground stops you from doing what the universe wants you to do. Fall. That thought did not arrive in a vacuum. More than 300 years before Einstein's afternoon in Bern, a showman in Italy had already planted the seed that would grow into the crisis. His name was Galileo Galilei, and Galileo grasped a principle that every showman knows. If you want to kill a bad idea, kill the bad idea where everyone can see. The target was ancient. For nearly 2,000 years, the Western world had operated under a single assumption about falling objects. Aristotle, the philosopher whose authority shaped European thought for 20 centuries, had declared that heavy objects fall faster than light ones. The claim made intuitive sense. Drop a cannonball and a feather from the same height in open air, and the cannonball hits first. Aristotle's followers accepted the claim without serious challenge, and the claim became embedded generation after generation in the curriculum of every European university. Questioning Aristotle was not merely unpopular, questioning Aristotle was closer to professional suicide. Galileo saw the flaw, and Galileo did not just see the flaw quietly. Galileo constructed a logical argument so clean and so devastating that the argument could demolish Aristotle without a single experiment. Imagine tying a heavy stone to a light stone with a rope. According to Aristotle, the combined object is heavier and should therefore fall faster. But wait, the light stone should also drag on the heavy stone, slowing the heavy stone down. So the combined object should simultaneously fall faster and slower than the heavy stone alone. The contradiction is total. Aristotle's framework collapses under the framework's own logic. But Galileo wanted more than logic. Galileo wanted theater. According to his student, Vincenzo Viviani, who recalled the story decades later, long after caring for the elderly and blind Galileo during house arrest at Arcetri, Galileo climbed the Leaning Tower of Pisa, gathered an audience of professors and students, and dropped objects of different weights from the top. Galileo already knew what would happen. Galileo's demonstration was not an experiment. The whole spectacle was a public execution of a 2,000-year-old idea, performed with what Viviani described as Galileo's flair for the dramatic. Every object landed at the same time, heavy and light, same speed, same impact. The professors watched the foundation of Aristotelian physics shatter against the ground. Most historians debate whether the tower event happened exactly as Viviani described. The details might be embellished. Viviani was recalling conversations from decades earlier, conducted with a man who was elderly and blind by the time the two met. But the result was never in doubt. Galileo had already confirmed the principle through careful laboratory work with inclined planes, measuring the acceleration of rolling balls with extraordinary precision for the era. And later, in prison in 1638, Galileo returned to the argument in the dialogue concerning two new sciences, building the logical case with such care that the reasoning still stands 4 centuries later. The tower, real or dramatized, was the exclamation point, the final punctuation, at the end of a sentence that physics had been writing for years. All objects fall at the same rate, regardless of mass. Period. And nobody asked the obvious question. For 3 centuries after Galileo, nobody paused to wonder why that result was strange. Because the result is deeply, profoundly strange. Think about every other force you have ever encountered. Push a heavy box and a light box with the same strength. The light box accelerates faster. Slam a baseball bat into a bowling ball, then into a tennis ball with the same swing. The tennis ball flies farther. Every force in nature affects objects differently depending on the mass of the object. Every force except gravity. Gravity treats a feather and a cannonball, a grain of sand and a planet, a proton and a star with absolute democratic equality. Every single object accelerates at exactly the same rate in the same gravitational field. That fact alone should have set off alarms for 300 years. The fact did not. Newton saw the pattern but missed the message. In 1687, Isaac Newton published the Principia, a masterwork that gave humanity the equation for gravitational force. The equation worked brilliantly. Planets obeyed, comets submitted, and tides arrived on schedule. For 2 centuries, Newton's equation stood as one of the most successful descriptions in the history of science. Newton even tested the question directly. He swung pendulums made of gold, silver, lead, iron, glass, salt, and wheat. Newton filled hollow bobs with each substance, measuring whether the period changed with the material inside. Every material gave the same result, and Newton recognized that the equality between how much an object resists acceleration, called inertial mass, and how strongly an object responds to gravity, called gravitational mass, was an extraordinary coincidence. Newton recorded the coincidence and used the coincidence in every calculation. But the deeper question, why inertial mass and gravitational mass match perfectly in every experiment ever conducted, haunted Newton without resolution. That unanswered question is the crack in the foundation. Newton described gravity as a force, an invisible pull reaching across empty space, acting instantaneously across any distance. For 200 years, the equation gave the right numbers for every observation thrown against the equation. Astronomers used the equation to predict the return of comets. Engineers used the equation to calculate the trajectory of artillery. The equation was the gold standard of physical law, the benchmark against which every other theory was measured. But ask what the force actually is, how the force operates, what mechanism carries the force from the sun to the earth across 150 million kilometers of vacuum, and Newton had no answer. Newton openly admitted the gap. In a letter to Richard Bentley in 1693, Newton wrote that the idea of one body acting on another through a vacuum without any mediation was so great an absurdity that no competent thinker could ever fall into the belief. The architect of the most successful theory of gravity in history, standing inside the theory's own framework, called the central mechanism absurd. And now bring the story back to the person falling from the building. Newton's equation says that person is being pulled downward by a force. The equation gives the precise magnitude of the force. The equation predicts the exact speed at which the person will hit the ground. But the person feels nothing. Every sensor the person carries reads 0. The pull that Newton described, the force that Newton admitted he could not explain, is invisible to the one object the force is supposedly acting upon. Push someone, and the person feels the shove against the chest. Pull someone's arm, and the person feels the tug. But a falling person reports nothing at all, not the faintest whisper of a force. The falling person still feels nothing. That silence, the total absence of any detectable force during freefall, is the clue nobody can explain away. Einstein recognized what the silence was telling him. If every object responds to gravity identically, regardless of mass, regardless of composition, regardless of any physical or chemical property the object possesses, then gravity cannot be a force acting on objects from outside. Gravity must be a property of the space the objects move through. The coincidence that Newton recorded and could not explain was not a coincidence at all. The coincidence was the single most important clue in all of physics, sitting in plain sight for 300 years, waiting for someone to decipher the message. A force would treat different objects differently. Only a property of space itself would treat every object the same. That equality. The equality Galileo demonstrated and Newton measured and neither could explain, was the Rosetta Stone of gravity. and the stone had been sitting on the shelf gathering dust since 1687. Einstein later listed the most important scientific ideas of his life, and the daydream from the patent office sat at the very top of the list, above the final equations from 1915. The insight about the falling person was not a footnote in the story. The insight was the foundation. And the replacement answer, the beautiful geometric picture that the world eventually adopted, arrived with a crack already forming inside the structure. Because Einstein did not stop at that one insight. Einstein spent the next 8 years building a mathematical framework that replaced force with geometry, that replaced pulling with curving. And when the framework was finished, when the equations were published in 1915, the equations produced the result nobody expected. The equations cracked open a question, one that Einstein himself would eventually confront, pointing toward two rival descriptions of gravity that the standard version could not accommodate. The official answer was barely a decade old before the answer started to fracture. But that fracture belongs to the next chapter of the investigation. Right now, the case file contains one entry, the most familiar sensation in human experience, the feeling of weight, of being pressed into a chair, of objects falling when released, describes a force that a falling person cannot detect. 3 centuries of physics gave that sensation a name, an equation, and a number. None of those tools ever explained what the sensation actually is. And the question hanging over this entire case, the one question that matters, is blunt. If you cannot feel a force, does the force exist? That question haunted Einstein for the rest of his life. Whether a force that no falling person can feel, a force invisible to every nerve in the body, deserves to be called a force at all. And the replacement answer that the physics community eventually adopted, the gorgeous picture of planets tracing curves through bent geometry, arrived with a crack. Nobody noticed for decades. Because the curved story was never the only story, 2 competing accounts of gravity existed, each built on completely different mathematics, each producing the exact same predictions. And the person who painted the most famous map quietly tried, before the paint had dried, to replace that map entirely. Here is the official record. In 1915, Einstein published the field equations of general relativity. Mass and energy warp the fabric of space and time. Objects follow those warps. The equations pass every test thrown against the equations for a century. Starlight bent around the sun during the 1919 eclipse. Gravitational waves rippled across 1 billion light-years, reaching the LIGO detector in 2015. Mercury's orbit, a puzzle that Newton could never solve, snapped into perfect agreement. By any reasonable standard, the case was closed. Curved space described gravity, and the search appeared to be over. But here is the problem. The case was never actually closed. Because the evidence that confirmed those equations did not confirm the geometry behind the equations. The evidence confirmed the math, and those same equations, the exact same mathematics that predicted Mercury's orbit, gravitational waves, and the bending of starlight, can be written in 2 other geometric languages, each built on a completely different picture of reality. The world celebrated one answer. The mathematics permitted 3. I need to slow down here and explain what different geometry actually means, because the phrase sounds abstract until you see the picture. Imagine 3 cartographers mapping the same island. The first draws the island on a curved surface, like the skin of a globe, and explains that travelers follow curved paths because the surface bends. The second draws the island on a flat sheet of paper, twisted and folded, so that straight lines on the paper trace, point by point, the same paths that appeared on the globe. A third uses a flat, untwisted sheet, but the ruler keeps changing length from place to place. Every map produces the same travel routes. Every map predicts the same distances between villages. Not a single measurement would reveal which cartographer drew the correct version. Bending versus twisting versus stretching. 3 stories about the same island. The first of those alternatives, the twisting one, has a name. Physicists call the theory teleparallel gravity. The word means parallel at a distance, a reference to the property that makes the theory work. Objects that start out moving in the same direction stay parallel, even across vast distances. because the space those objects move through is flat. Curves vanish entirely, completely. The geometry that replaces curves is torsion, a property describing how space can twist without curving. In the standard picture, the fabric curves but does not twist. In the twisting picture, the fabric twists but does not curve. Two completely opposite geometric assumptions. Yet the equations match perfectly, the predictions align, and the observable universe appears the same under both models. And the story behind that alternative is stranger than the alternative itself. No rebel outsider built the twisting version to dismantle the establishment. The person who explored the idea, who wrote the letters, published the papers, and chased the mathematics to the edge of failure was the architect of curved space, Albert Einstein. In 1928, barely 13 years after publishing General Relativity, Einstein began corresponding with a French mathematician named Élie Cartan. The geometer was not a physicist. Cartan was one of the foremost mathematicians of the 20th century, a scholar who had developed the tools for describing torsion, publishing the foundational papers in 1922 and 1923. The work described how connections on abstract spaces could carry antisymmetric properties, properties that the standard Levi-Civita connection did not possess. Einstein studied those papers and saw a possibility that nobody else had noticed. The insight was radical. A flat space equipped with torsion could accomplish what bent space could not. The flat space model in that vision could unify gravity and electromagnetism into a single geometric system. The 6 extra degrees of freedom in the twisting formulation, 6 variables that the standard theory of gravity did not have, looked like the perfect hiding place for the electromagnetic field. Think about the ambition of that project. The most famous physicist alive was writing private letters to a geometer, exploring a theory of gravity that made curves completely unnecessary. That ambition was staggering. The physicist was not adjusting a dial or refining a detail. Instead, Einstein was attempting quietly and deliberately to demolish the very foundation of a building that bore his own name. And from the wreckage, the architect of bent space planned to assemble, from the wreckage, a structure that nobody on Earth had ever encountered. The correspondence stretched across years, filling dozens of letters with dense arguments, corrections, and mutual challenges. The letters revealed 2 brilliant minds wrestling with geometry at the highest level. One, a physicist chasing a grand vision, the other, a geometer insisting on rigor. Einstein published 2 papers on the flat space formulation in 1928 and returned to the topic in 1930. The project made headlines. Newspapers reported that the physicist was working on a new theory. Colleagues around the world paid attention, but the excitement collapsed when other physicists examined the equations and reached a devastating conclusion. The torsion-based version produced no new predictions. Every observable quantity the twisting model calculated matched the curved model exactly. The alternative was not wrong. The competing theory was redundant, at least by the standards of the 1930s. Colleagues and critics, after examining the equations, convinced the physicist that the flat space approach offered no experimental advantage. The hope of capturing electromagnetism in those extra degrees of freedom had not materialized. Einstein abandoned the project. And here is the joke the universe played on everyone involved. The physicist was right to try and wrong to quit. The abandoned work would turn out decades later to be a genuine, rigorous alternative, matching every prediction of general relativity. Mathematically, the work was sound. Physically, every prediction matched. Einstein's only flaw was the reason for starting the project in the first place, but the instinct about the mathematics was correct. Only the motivation, the hope of cramming electromagnetism into the same geometric package, was flawed. After Einstein walked away, the twisting alternative entered a long winter. For decades, the flat space contender sat in the archives of mathematical physics, gathering dust. The idea was dismissed as a curiosity, a historical footnote about a genius who chased unified field theories that never panned out. Textbooks taught curvature. Lecture halls echoed with the language of curved space. Graduate students learned to calculate with the Levi-Civita connection, the standard machinery of general relativity. and that connection carried zero torsion by definition. The entire discipline of gravitational physics built a century of understanding on one picture. Mass bends space, objects follow the bends, and any other account was a dead end already explored and rejected. Nobody questioned the assumption. The preference for bending was baked into the pedagogy, the textbooks, the hiring committees, the grant applications. Asking, "Is space really curved?" was not controversial. The question was not even considered worth asking. Generations of physicists inherited the curved model the same way children inherit an accent, without choosing the accent, without realizing alternatives existed, and without any reason to wonder whether the accent was the only way to speak. The winter lasted half a century, and then, slowly, the ice began to crack. In the 1970s and 80s, physicists in Brazil and Japan began revisiting the torsion-based formalism with fresh eyes. Researchers like José Pereira at the Universidade Estadual Paulista and Kenji Hayashi in Tokyo returned to the structure that Einstein and Cartan had abandoned. But these researchers had no interest in unification. The researchers stripped away the grand ambitions, the dream of cramming electromagnetism into 6 spare variables, and asked a simpler question: does the twisting formulation describe gravity accurately on the terms gravity already set? Pereira and collaborators rebuilt the formalism from the ground up, using modern mathematical tools that Einstein and Cartan had not possessed half a century earlier. The calculations took years, the checking took longer, and when the results were complete, the answer was unambiguous. Yes, the twisting version reproduces every prediction of general relativity, not approximately, not in certain limits, every single prediction. Rigorous and peer-reviewed, the work was largely ignored by the broader community because mainstream physics had already decided that curvature was the only viable account. Papers sat in journals, gathering citations slowly, a quiet revival that almost nobody outside the specialist community noticed. Mainstream physics kept teaching curved space. Textbooks stayed exactly the same. But in the 2000s, the trickle became a stream. A new generation of physicists, armed with modern tools and motivated by open questions in quantum gravity and cosmology, returned to the abandoned formulation. And what those researchers proved should have shaken the discipline to the roots. The twisting contender is not a curiosity and not an approximation. Every classical field equation matches the standard equations precisely. The actions of the two theories, the quantities physicists use to derive the equations of motion, differ only by what is called a boundary term, a quantity that changes the action but does not change the physics. Such a term does not affect the equations of motion, does not alter any prediction, and remains invisible to every experiment ever conducted. In the language of physics, two theories whose actions differ by a boundary term are classically equivalent. Both generate the same field equations, the same solutions, the same observable universe. Choosing between the two is not a scientific judgment. Choosing is a preference for one language over another. Now, I wanted to believe that two competing theories was already strange enough, but the universe, apparently, has a taste for symmetry. In 2018, a team of physicists including José Beltrán Jiménez, Lavinia Heisenberg, and Tommy Koivisto published a paper that should have made front-page news but barely caused a ripple outside specialist journals. Together, those researchers formalized yet another geometric account of gravity, a third way of writing the same equations using a third type of geometry. They called the result coincident general relativity, though the result is also known as symmetric teleparallel gravity or the non-metricity formulation. The geometric idea behind this third formulation is different from both of the others, and I still find the concept difficult to hold in my head. In this third account, space is flat, zero curvature. Space is also twist-free, zero torsion. But rulers change. Distances measured by physical instruments shift from place to place, stretched or compressed by the presence of mass and energy. The property responsible for gravity in this model is called non-metricity, and the name refers to the fact that the standard method of measuring distance, the metric, stops being preserved when you move from one point to another. Space does not bend. Space does not twist. The measuring sticks warp. Carry a ruler from one side of a room to the other, and the ruler is a slightly different length when the ruler arrives, changed by the gravitational field without the ruler ever touching anything. In this model, the universe keeps the books balanced, not by curving the road, not by twisting the road, but by quietly redefining what a meter means depending on where you stand. Physicists now call all three theories together the geometric trinity of gravity. That name is not casual. A structure connects the three, with each corner representing a different geometric property: curvature, torsion, or non-metricity. Each corner gives rise to an equivalent description of the gravitational field. All three sit at the vertices of a triangle, connected by the boundary terms that make the theories classically indistinguishable. Three theories: curving, twisting, warping the rulers. And no experiment, no observation, no measurement ever performed can tell the three apart. Look at what that means in practice. A student walks into a physics classroom in 2026, opens a textbook, and encounters the claim that gravity is the curvature of space and time. The claim seems definitive, and the claim is true in the sense that the equations work, but the statement is also incomplete in a way the textbook never mentions, because two other geometric accounts produce the same equations, the same predictions, and the same experimental confirmations. That student learns one account and never hears that two alternatives exist. No conspiracy explains the gap in the curriculum. Pure inertia does. Physics chose a language a century ago and has never found a reason to switch, because no experiment can provide that reason. Not the mathematics, the implication. The world taught you that space is curved. Every science documentary you have watched, every textbook you have opened, every physics class you have attended presented curvature as the answer. And the answer is real. The bending works. But bending is one answer among three, and the other two answers work just as well. And nobody in the entire history of experimental physics has ever devised a measurement that can distinguish between the three. I have spent weeks looking for a way to break the tie, and the results are not encouraging. The equivalence principle holds to a precision of 1 part in 10 trillion. All three geometric accounts honor that principle with equal fidelity. No proposed observation from light deflection to orbital precession can separate the three. The reason for preferring one version over the other two is not scientific. History made the choice, not evidence. General relativity came first. Physics built a century of education, research, and intuition on that single theory. Einstein explored and abandoned the twisting alternative. Nobody formalized the non-metricity account until decades later. Every preference for curvature is an artifact of chronology, not evidence. Sebastian Bahamonde and Mir Faisal, in a prize-winning essay for the Gravity Research Foundation in 2019, stated the conclusion bluntly. The only reason for the preferential attention given to general relativity over the other two geometrical theories is historical and not scientific. That conclusion should feel like the floor dropping out from under you. What you trusted, the explanation printed in every physics textbook in every language on Earth, is not a definitive answer. Curvature is one of three accounts, and the choice between the three might be a question of taste rather than truth. And the philosophical consequences run deeper than a debate about which math is more elegant. Philosophers of physics at Cambridge and Oxford, researchers like Mulder and James Reed, have spent years arguing about whether the underdetermination between these three theories is genuine. The question those philosophers are asking is sharper than any equation. Does the existence of three equivalent alternatives mean, definitively, that the bending of space is not a physical fact about the universe? Does the standard picture describe a real property of nature, or does the standard account describe instead a feature of the language, the mathematical dialect that humans happen to choose first? Maybe the curves are genuinely out there, woven into reality, or maybe the curves are a convention, like choosing to draw a map with north at the top. And no measurement, no observation, no experiment in the history of science can settle the question. You are standing at a fork with three roads stretching ahead of you. Each road reaches the same destination. All three pass the same landmarks. Walking any of the three takes the same amount of time. But the three roads do not agree on why you are moving. The first says the ground is curved beneath your feet. The second says the ground is flat but twisting you sideways. And the third says the ground is flat and straight, but the steps you take keep changing size. You cannot tell which road you're actually on because every measurement you take gives the same answer regardless. That vertigo is not an accident. The vertigo is the point. The feeling of standing on ground that could be curved, could be twisted, could be stretching the ruler beneath your feet with no way to know which story is true. That feeling is the honest state of knowledge in gravitational physics today. 3 maps, same predictions, no experiment can choose. The question is still open. But the story of how gravity lost a single definitive answer, as unsettling as that story is, represents only half the crisis. Because the person who started the curvature story, the person whose name sits at the top of every textbook explanation, did not agree with how the world teaches the theory. That disagreement was not a footnote. The rift was fundamental, and the rift was buried, ignored, and forgotten for close to a century. The evidence for that betrayal has been hiding in plain sight in papers and letters and notebooks that the physics community overlooked for generations. And the betrayal is next. Notes and letters and old papers, the betrayal was never hidden behind a locked door or buried in a classified archive. Every piece of evidence sat in the open, published, translated, and available to anyone who cared to look. And for close to a century, almost nobody looked. Here is what the physics community missed. Einstein did not believe that gravity is the curvature of space-time. That sentence probably sounds wrong. Every textbook on Earth says the opposite. Every science documentary ever broadcast describes gravity as bending, as warping, as the reshaping of a 4-dimensional fabric. The phrase, mass curbs space, has been printed so many times in so many languages that the phrase has achieved the status of a fact nobody questions. Walk into any physics classroom on the planet and ask the professor what gravity is. The answer will be bending. A diagram will appear on the board. Mass warps the fabric of space and time, the professor will explain. And the professor will be repeating a reading of the framework that the creator rejected. Einstein identified gravity with the motion of freely falling bodies, not with bending and not with tidal stretching, with the motion itself. That distinction matters more than any equation in this entire story. And the distinction has been buried under a century of textbook repetition so complete, so thorough, so universally reinforced, that the burial looks like a feature of the terrain rather than a concealment. I want to walk you through the evidence slowly, because the evidence is damning, and because the evidence changes the meaning of every claim, every explanation the investigation has uncovered so far. In 2002, a physicist named Peter Brown sat down at a desk and did what should have been done decades earlier. Brown did not discover new physics. Brown did not propose a new framework or design a new experiment. What Brown did was simpler and, in many ways, more devastating than any of those alternatives. Brown went back to Einstein's own publications, the original papers, the letters, the lecture transcripts, and studied what Einstein actually wrote, word by word, sentence by sentence. Then Brown compared those words to what the modern physics community teaches in classrooms, in textbooks, in review articles. What emerged was not small, not a matter of emphasis or framing. Brown had uncovered a fundamental disagreement about what gravity is. The disagreement starts in the mathematics, and the disagreement will crack the foundation of a century of teaching. General relativity uses a set of quantities called the Christoffel symbols, or more formally, the components of the affine connection. These quantities describe how objects deviate from straight-line motion through space-time. Think of the quantities as invisible road markers. When all the markers equal 0, a traveler moves in a straight line. When the markers are not 0, the path bends. Einstein looked at those markers and made a declaration that left no room for ambiguity. In the 1916 review paper, the landmark publication that presented general relativity in complete form for the first time, Einstein wrote that the Christoffel symbols are the components of the gravitational field. The designation was not casual. The label was not a metaphor. Einstein was identifying a specific quantity with a specific physical phenomenon. Wherever the components of the affine connection do not vanish, the field exists. Wherever those components are zero, the field is absent. A particle that deviates from straight motion is moving through a gravitational field. No deviation means empty space. That distinction for Einstein was the entire substance of what gravity means. Now here is where the confusion entered the record. A completely different quantity, the Riemann curvature tensor, measures whether space-time itself is bent. The Riemann tensor detects stretching and squeezing effects, the forces that pull one side of a body more strongly than the opposite side. Nobody disputes the physical reality of those effects. The tensor measures the effects with exquisite precision, and the machinery has earned a permanent place in gravitational physics. But then, in the decades after Einstein published the equations, the broader physics community made a fateful substitution. The change was so gradual that the substitution looked natural. Physicists began identifying gravity not with the deviation markers that Einstein had named, not with the affine connection, but with the Riemann tensor. Gravity became tidal stretching, and the field became space-time warping. Textbooks printed the new definition. Professors taught the new definition to graduate students. Those graduate students became professors and taught the definition to the next generation. And the account Einstein had published, the position Einstein had argued for in print across 4 decades of active scientific work, was overwritten. None of that process was deliberate sabotage. No committee ever voted to replace Einstein's definition, and no calculated decision was made in a smoke-filled room. Instead, the substitution happened. The way most errors in institutional knowledge happen, slowly, invisibly, one lecture at a time, one textbook revision at a time, one graduate student at a time, until the replacement was so deeply embedded, so thoroughly normalized, that questioning the replacement felt like questioning gravity itself. And the overwriting created a contradiction, so fundamental that an undergraduate should have caught the problem. The equivalence principle, the very foundation upon which general relativity was built, describes a situation in which an observer cannot distinguish in any way between standing in a gravitational field and accelerating through empty space. That situation requires a uniform field. A uniform field has no gradients, zero stretching, zero warping. Under the modern account, which defines gravity as the Riemann tensor, a uniform field of gravity becomes a contradiction in terms. Gravity, in a place where gravity cannot exist, the foundation buckled under the weight of a definition the community had chosen for convenience. Under Einstein's original account, no contradiction arises. A uniform field has zero curvature but non-zero components of the affine connection. The falling person feels no force. The connection markers are not zero. Gravity exists. No bending required. The principle works exactly as Einstein advertised. And yet, that contradiction sat in the literature for decades without correction. Not a single reviewer flagged the problem. No textbook author raised the issue in a preface, and no editorial board pulled the emergency brake. The two definitions, the one Einstein intended and the one the community adopted, coexisted in the same journals, the same departments, sometimes the same paragraphs, without anyone acknowledging that the two definitions describe different physical situations and produce a logical conflict at the very foundation of the equations. And Einstein did not accept the substitution without a fight. The confrontation has a name and a date attached. Max von Laue was one of the most respected physicists of the early 20th century, a Nobel laureate whose work on X-ray crystallography had earned the highest honors in the discipline. Von Laue stated publicly and emphatically that the Riemann tensor was the only legitimate representation of the field. If the Riemann tensor vanishes, von Laue argued, gravity vanishes. Period. Einstein's response was sharp. In a written reply that Peter Brown unearthed and quoted directly, Einstein insisted that what characterizes the existence of a gravitational field from the empirical standpoint is the non-vanishing of the components of the affine connection, not the non-vanishing of the Riemann tensor. That sentence alone should have stopped the drift. The creator of the framework, responding to a direct challenge from a Nobel laureate, stated in writing that the standard reading was wrong. But Einstein did not stop with the correction. Einstein pressed the argument further into territory that should have alarmed every physicist who encountered the exchange. If a person does not think in such intuitive ways, Einstein wrote, that person cannot grasp why curvature of all concepts should have anything at all to do with gravitation. In any case, no rational person would have hit upon the connection otherwise. Without that intuition, the key to understanding gravitational and inertial mass and the equality between the two would have been missing entirely. The implication is staggering. Pause on the scene for a moment. In a direct exchange with a fellow Nobel laureate, the architect of general relativity declared plainly that the curved account rendered the origin of the entire architecture incomprehensible, completely opaque. The curved lens obscured the very insight, the equivalence of inertial and gravitational mass that had made the whole enterprise possible in the first place. And the physics community, after recording the exchange in the open literature, continued teaching the standard version as though the objection had never been raised. But the disagreement with von Laue was only one skirmish in a much larger war. Dennis Lemkuhl, a philosopher of physics at the University of Bonn, spent years tracing the evolution of the foundational claim across Einstein's published and unpublished writings. Lemkuhl arrived at a conclusion that rewrites the standard history. Einstein's equivalence principle is intimately linked to a radical idea. Gravity and inertia are unified into a single field, the same way that electric and magnetic fields had been unified by special relativistic electrodynamics. The unification is not a metaphor or a loose analogy. Einstein saw the gravitational phenomenon and the inertial phenomenon as one entity, two names for the same physical reality, inseparable. Electricity and magnetism become inseparable once a person accepts special relativity. Gravity and inertia, in Einstein's view, follow the same pattern. An observer in a sealed room cannot distinguish by any measurement between the room accelerating upward and the room sitting stationary in a gravitational field. For Einstein, that sameness was not a clever thought experiment to be filed away after a lecture. The sameness was the physical substance of the whole structure. Gravity and inertia are one phenomenon. The principle is the declaration that the two cannot be separated. What textbooks now call the strong equivalence principle asserts a different claim. The strong version holds that general relativity is locally special, relativistic, meaning that in a sufficiently small region of space-time, the laws of special relativity hold with arbitrary accuracy. That assertion is true, demonstrable from the mathematics, and present in every modern textbook on gravitation. And yet the assertion is not what Einstein meant by the foundational claim. Einstein carefully distinguished the two ideas in every major publication, spanning the years from 1907 through the early 1950s. The distinction was not pedantic. Einstein gave the two ideas different names and assigned the two ideas different roles in the architecture of the equations. And yet, over the course of 3 academic generations, the physics community merged the two principles into one, discarded the original version, and stamped Einstein's name on the replacement. The historian of physics, John Norton, working at the University of Pittsburgh, documented the divergence with the precision of a forensic accountant going through 50 years of financial records. The conclusion was damning. Norton demonstrated that Einstein's formulation and the way Einstein sought to deploy the principle are essentially different from the many later versions that bear the same name. Every objection that later physicists raised against the foundational claim turned out to be peripheral. The claim is merely approximate, those critics argued. Stretching forces, those critics insisted, expose the claim as nothing more than a convenient fiction. But all of those complaints targeted the replacement, not the original. Einstein's version finds, in Norton's words, completely satisfactory and uncontroversial expression in the finished general relativistic framework. No flaw existed in the original. Instead, the community replaced the principle with a different one, then spent decades criticizing the replacement for limitations that belonged to the replacement alone. I have been sitting with the primary sources for weeks, and the pattern that emerges is not dramatic in the way a conspiracy is dramatic. The pattern is banal. The confusion arrived through the ordinary machinery of academic inheritance. One generation of physicists interpreted the equations in a certain way, wrote the textbooks, trained the next cohort of graduate students, and retired. Those students inherited the reading, without knowing the reading had been contested by the architect. In time, those students became professors, and those professors trained the next class. Each generation received the message a little further from the original transmission, a little more colored by the assumptions of the person delivering the lecture, a little more divorced from the specific words Einstein had written. By the time Peter Brown sat down in 2002 and traced the paper trail, the divergence between Einstein's actual stated position and the world's standard teaching had been compounding, unchallenged and uncorrected for close to 90 years. A century-long game of telephone, and the message that arrived at the end bore almost no resemblance to what the sender transmitted. But here is the thing that makes the betrayal personal instead of academic. Remember the prank from 1919, the colorful story Einstein spun for the New York Times correspondent, the tale about watching a man tumble from a roof onto a heap of garbage. The correspondent published the dramatized version without realizing the physicist was amusing himself. That joke contaminated the historical record. Generations of writers copied the anecdote as fact, and the joke became the origin story the world remembered, while the real origin, the quiet afternoon in the patent office in Bern, the mental image of a person falling through absolute silence, the leap from that silence to the equivalence of gravity and inertia, slipped out of the popular narrative, settling into the footnotes where only specialists could find the real story. Einstein did not consider that origin a footnote. Galeno Weinstein, investigating Einstein's pathway to the equivalence principle, recovered a document from 1921, a document that settles the question of priorities with no room for debate. Einstein wrote a short list, cataloging what he considered the most important scientific ideas of his entire career. 3 entries closed the list. 1907, basic idea for the general description of gravitation. 1912, recognition of non-Euclidean geometry and the physical determination of the metric by gravitation. 1915, field equations of gravitation, explanation of the perihelion motion of Mercury. The basic idea. Above the final equations and the triumphant predictions, higher than the geometric framework the world would celebrate for a century, the daydream about falling, the realization that a person in free fall experiences no gravitational force, the leap from that observation to the unification of gravity and inertia, occupied the first position on the list. Einstein ranked the 1907 insight above the recognition of curved geometry, above the formalism from 1912, above the field equations from 1915, and above the explanation of Mercury's anomalous orbit. The architect ranked the daydream above the building. And then, in June of 1933, Einstein traveled to Glasgow to deliver the university's first George Gibson lecture, Bute Hall. An audience of physicists, mathematicians, and university officials, a visiting lecturer speaking in English for 20 minutes about the origins of general relativity. Einstein's manuscript, written in German, carries a title that translates roughly as Notes on the Origin of the General Description of Gravitation. In that lecture, Einstein retraced the intellectual pathway from special relativity to general relativity. And that pathway does not begin with curved geometry. Instead, the pathway begins with a failure. Einstein described how early attempts to incorporate gravity into special relativity had produced flawed equations. Bodies of different compositions fell at different rates in those equations, a direct violation of Galileo's law of equal acceleration. The law of the equality of inertial and gravitational mass illuminated Einstein, he told the Glasgow audience. That law aroused a suspicion, Einstein said, that the equality must contain the key to a deeper understanding of inertia and gravitation. That Glasgow lecture is the closest the historical record comes to a confession. Einstein was not simplifying for a popular audience or entertaining a journalist with a colorful anecdote. Instead, Einstein was speaking to peers in a university lecture hall, manuscript in hand, with the full weight of the physics establishment listening. And the pathway Einstein described runs through the silence of freefall, through the equivalence of gravity and inertia. A falling person and a floating person, Einstein insisted, are physically identical, not through curvature, not through the bending of a four-dimensional fabric, through the simple, devastating observation that a falling person cannot detect any force at all. Einstein had placed that observation at the top of the list 13 years earlier, and the 1919 prank had buried that observation under a joke about a man landing in garbage. Meanwhile, the world heard a completely different story. Textbooks taught that mass curved space, and documentaries showed rubber sheets deforming under bowling balls. Across every campus on Earth, every lecture hall echoed with the language of Riemannian geometry, the vocabulary of warping and curving. Graduate students learned to calculate using a connection that carries zero torsion by definition. Not one of those students ever questioned why torsion was excluded or what the exclusion might be hiding. An entire discipline built a century of understanding on one picture, the picture of curved space. And the person who painted that picture, the architect himself, walked away from that account before the century had begun. The architect drew the map and then walked away from the map. The world kept following the version the architect abandoned. That is the betrayal. That single word captures what sits at the center of this investigation. Not a secret discovered in a dusty archive, not a conspiracy exposed by a whistleblower. A slow, systemic, generational drift away from what the creator actually believed, carried by the inertia of textbooks, amplified by the convenience of pedagogy, and cemented by the sheer mass of accumulated repetition. The most celebrated scientific achievement in human history has been taught for 100 years in a way that the architect explicitly and repeatedly rejected. And the rejection was not whispered in private correspondence or confided to a diary. The rejection was published, argued, and defended in the open literature, in Einstein's own words, across 40 years of active scientific life. 3 indistinguishable maps of reality. An architect who rejected the most popular map, a century of physics that never noticed the disagreement. And the ground beneath the standard teaching of gravity did not crack today. That ground cracked before most people alive were born. Nobody ever looked down. But the investigation does not end with a disagreement about how to frame the equations. Because if the architect was right, if gravity is the motion of falling rather than the warping of a geometric fabric, then the sensation pressing against the viewer's body at this very moment, the weight, the downward pull, the familiar pressure of solid ground might not be what the sensation appears to be. The sensation might emerge from a substrate deeper than any geometry, a phenomenon nobody has managed to name, a phenomenon that dissolves the fabric of space itself into a foundation no instrument has ever measured. And that dissolution is next. So what is left? That question that nobody in the mainstream had bothered to ask. If the architect rejected the bending, and if 2 rival geometric languages match every observation, then what exactly is left? A force that a falling person cannot feel. 3 maps exist, and no experiment on Earth can tell the 3 apart. A creator who rejected the reading the world adopted. Each layer of certainty about that sensation, the most familiar in human experience, has cracked under the weight of evidence. And now, at the bottom of the stack, one more layer remains. The deepest layer, the assumption that gravity is a fundamental property of the universe at all. A warning is necessary before we go further, because the claim about to emerge from the evidence is not settled science. The claim is a provocation, a formal case published by a respected physicist, taken seriously by some of the sharpest minds in theoretical physics, and dismissed by others with equal conviction. The investigation has earned the right to present the case, because every comfortable explanation has already cracked. But intellectual honesty demands caution. What follows is speculative, and the evidence is suggestive rather than conclusive. And the implications, if the reasoning survives scrutiny, are the strangest in this entire investigation. The idea arrived in January of 2010, and the idea arrived from a direction that nobody in the gravity community expected. Eric Verlinde was not a specialist in general relativity. The physicist was a string theorist at the University of Amsterdam, a researcher whose career had been spent deep inside the abstract terrain of quantum gravity. The paper Verlinde posted that January carried an unassuming title, On the Origin of Gravity and the Laws of Newton. 0 experiments proposed and not a single new particle predicted. No billion-dollar detector required. Just mathematics and a single devastating idea. The paper hit the physics world like cold water thrown on a sleeping face. Gravity, the string theorist wrote, is not a fundamental force. Not the bending of space, and not the twisting either. Certainly not the stretching of rulers. None of the geometric accounts capture what gravity actually is. The pull that holds planets in orbit, that pins you to your chair, that dragged every apple from every tree since trees first grew on Earth, is not woven into the fabric of reality. The pull is a side effect, a consequence, a mirage created by processes deeper than any current vocabulary can reach. Gravity, in the Amsterdam physicist picture, is an entropic force. That phrase needs unpacking because the phrase sounds technical, and the meaning behind the phrase is the opposite of dry. Right now, the air around you has warmth. You can measure the warmth with a thermometer, predict the forecast with weather models, feel the heat on your skin. Warmth seems real, fundamental even, but warmth is not a property that exists at the deepest level of physics. No single molecule has warmth. A thermal state emerges when billions of molecules bounce around randomly, and the collective behavior of those billions of collisions produces a statistical average. Humans experience that average as heat or cold. At the human scale, the thermal state is as real as the skin on your arm. At the molecular scale, the same state is an illusion. A thermometer measures a genuine quantity, but the effect being measured is a collective act staged by particles too small and too numerous to track individually. Verlinde proposed that gravity works the same way. The idea is elegant and terrifying in equal measure. Not as a force reaching across empty space the way Newton imagined, not as a property of the fabric the universe sits inside the way every textbook teaches. Gravity, in the entropic picture, emerges from a deeper substrate. Encoded states, the behavior of microscopic degrees of freedom written on surfaces, processed by rules that nobody has identified, producing the macroscopic effect that humans experience as weight. Right now, the pressure against your body in that chair, in the Amsterdam physicist's picture, is not caused by a force and not caused by a curve. Instead, the sensation arises from changes in stored data, changes associated with matter and with the positions of material bodies. And the mathematics remarkably works, not approximately, not in certain special limits, not under generous rounding. Every law that has governed gravitational physics for over 3 centuries falls out of the physicist's reasoning. Ingredients anchor the derivation. First, the holographic principle, which states that the maximum data in any volume of space can be encoded completely on the boundary surface of that volume. Second, the equipartition of energy, which distributes energy evenly among all available microscopic states, and a postulate borrowed from black hole physics, proposed decades earlier by Jacob Bekenstein, that a particle approaching a surface changes the entropy of that surface by a tiny, calculable amount. From those 3 ingredients, with no additional assumptions, the derivation produced Newton's law of gravitation, the inverse square law, the same equation that Newton published in 1687, the equation that predicted planetary orbits, tidal rhythms, and the paths of comets for 300 years. That equation fell out of the statistical derivation, the way a shadow falls from a lamppost. Not designed and not forced, but emergent. But the paper did not stop at Newton. The reasoning pushed into relativistic territory, showing that the same logic, generalized to include the full machinery of thermodynamics on holographic surfaces, produces the Einstein field equations. The same equations that general relativity uses. Those very equations predict the bending of starlight, the existence of gravitational waves, and the precession of Mercury's orbit. 2 entirely different starting points. One begins with curved geometry, building outward from Riemannian mathematics. Another begins with bits of encoded data written on holographic screens, building outward from thermodynamic principles. Both arrive at the same destination. Both reproduce the same observable universe, and no experiment performed to date can tell the 2 arrivals apart. The paper accumulated hundreds of citations within months. Physicists around the world began testing the claim, probing the assumptions, searching for the flaw that would collapse the proposal into a clever curiosity. Conferences devoted sessions to the idea. At the Perimeter Institute in Canada, a panel of researchers spent an entire afternoon dissecting the derivation, questioning whether the holographic postulate smuggled in shape-based assumptions through the back door. Graduate students at Amsterdam and at Harvard built entire thesis projects around the emergence model, testing every assumption the proof required. The idea had landed in the center of theoretical physics and refused to leave. I have been staring at the derivation for weeks, and the experience is disorienting. The logic moves from assumption to conclusion, with a clarity that forced me to check the assumptions 3 times. I was looking for hidden geometry, smuggled in through the back door. No geometry appears. Space in the information-based account is not fundamental. Space emerges. Holographic surfaces are not floating in a pre-existing void. Those surfaces generate the void. Matter does not sit inside space-time and warp the container. Instead, matter and the container arise together from a substrate that the current vocabulary of physics cannot name. The reaction from the physics community was immediate and divided. Within weeks, the paper had been downloaded tens of thousands of times. The string theorist, who had spent decades working in relatively quiet academic corridors, found himself fielding interview requests from major newspapers, science magazines, and television networks. The proposal had broken containment, leaping from specialist journals into the popular press with a speed that surprised even the author. Some theorists embraced the reasoning with open arms. The resemblance between gravitational formulas and thermodynamic expressions had been noticed for decades, stretching back to Bekenstein and Hawking, who explored black hole entropy in the 1970s. The connection was too persistent to be a coincidence, and the informational reading offered the first coherent explanation for why the resemblance exists. Gravity looks like thermodynamics because gravity is thermodynamics. The equations look alike because the relations describe the same underlying process: encoded states changing on surfaces, entropy increasing, and the macroscopic result arriving as a force that looks fundamental but is not. Others pushed back hard, and the objections were not dismissive, hand-waving from physicists protecting their turf. Every challenge was pointed, technical, and in some cases, devastating. One concern haunted the debate from the beginning. If gravity is an emergent effect driven by entropy, where is the microstructure? Warmth emerges from molecules. Sound emerges from vibrations in a physical medium. Every known emergent effect in the history of physics has an identifiable substrate. What is the substrate for gravity? The paper does not name the microscopic degrees of freedom. The calculation assumes the degrees of freedom exist, encodes the assumption in the holographic principle, and derives the macroscopic law. But the logical chain leaves the deepest concern unanswered. The molecules behind the warmth of gravity, if those molecules exist at all, remain invisible and unnamed. And the critics had sharper weapons. Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, published a detailed analysis contending that the Amsterdam conjecture faces a fundamental tension with quantum mechanics. Statistical forces, Hossenfelder pointed out, are dissipative by nature. A polymer in a heat bath, for example, loses energy to the surrounding environment as the polymer returns to equilibrium. If gravity is genuinely driven by entropy, where does the dissipated energy go? Orbiting planets do not lose energy through gravitational interaction, at least not at any detectable rate. After all, the solar system has been running for 4.5 billion years with extraordinary precision. A statistically driven force that bleeds energy should produce observable friction, and yet no such friction has ever shown up in any gravitational system. Verlinde responded. The distinction, the physicist contended, lies in 2 fundamentally different types of thermal behavior. The polymer example involves a system exchanging energy with a heat bath. Gravity, in the information-based picture, operates differently. The thermal state that drives the gravitational force arises from the Unruh effect, a quantum mechanical prediction. According to Unruh, an accelerating observer experiences a bath of particles, even in otherwise empty space. That Unruh radiation is not the warmth of a surrounding medium. Rather, Unruh radiation is a property of the acceleration itself. The Amsterdam researcher contended in response that the force arising from this particular kind of thermal state uniquely does not dissipate energy in the classical sense, because the bath is not a separate physical system. The bath is a feature of the observer's reference frame. That response did not satisfy everyone. Debate continued through journals, conferences, and seminar rooms across 3 continents. In 2016, the string theorist extended the logic with a longer paper, one that attempted to tackle dark matter, contending that the observed discrepancies in galactic rotation curves, the same discrepancies that motivated the dark matter hypothesis, emerged naturally from the emergence model without requiring any invisible mass. The claim was bold and controversial, reaching far beyond the original proposal. Some observational tests appeared to support the predictions. Others fell short of the mark. The verdict remains open, and the scientific community remains divided, unsure whether the extension strengthens or overextends the original idea. No experiment has confirmed the Amsterdam conjecture. No experiment has ruled the hypothesis out. The model sits in an uncomfortable middle ground, too mathematically clean to dismiss and too physically incomplete to accept. But here is the detail that landed hardest during my weeks with the primary sources, the detail that shifted the entire case into a different register. The information-based conjecture does not merely add a 4th option, one more line on the existing menu of curvature-related accounts. The hypothesis does not simply say, here is another way to write the field laws. The reasoning dissolves the menu entirely. Consider what that means. Curvature, torsion, non-metricity, the 3 geometric languages that match every experiment, all assume that gravity is fundamentally a property of shape. All 3 assume that space-time in some form is the arena where physics happens, and that gravity belongs to that arena. The Verlinde picture removes the arena. In that rendering, space is not the stage on which the show occurs. The fabric is part of the show. Every dimension, every coordinate, every measurable distance emerges from the same deep substrate that generates gravity. Remove the foundation, and space collapses alongside gravity into a condition that has no geometric rendering at all. A force vanished. 3 rival maps multiplied. An architect walked away from the building, and now the floor might not be solid. Every layer of certainty about gravity, from Newton's force to Einstein's curvature to the geometric trinity to the informational dissolution, has peeled away under the pressure of the findings. And each layer reveals not an answer, but a deeper puzzle. Now step back from the mathematics and feel the weight of what this investigation has uncovered. The sensation of gravity, the pressure against your feet, the pull you feel every waking second, the constant companion that has been present since the first moment of your life, might not be a force, might not be a property of the universe's geometry, and might not be a fundamental feature of reality at all. That sensation might be an artifact, a macroscopic mirage produced by microscopic processes that no instrument on Earth has ever detected. Your floor holds, the chair supports you. Both feet press against a surface, and the surface presses back. Every human instinct, every evolutionary calibration, every biological sensor in your body insists, without reservation, that the ground is solid and the downward pull is real. And the case has traced a path, evidence by evidence, layer by layer, from a man daydreaming in a patent office to a string theorist in Amsterdam, that leads to a single conclusion: nobody knows why the ground holds. Newton described the holding as a force and admitted the mechanism was absurd. Einstein described the holding as a property of geometry, then rejected the popular version of that geometry. 3 rival mathematical accounts match every observation, and nobody can tell the 3 apart. And now, the emergence conjecture says that geometry itself is not fundamental, that space emerges from encoded states, and that the familiar weight of your own body is a statistical effect produced by a process that no existing vocabulary can name. The ground has become a question, and the question is not abstract. The question is as concrete as the pressure beneath your feet at this very moment. Stand up if you can, and feel the floor pushing against you. That push has been your most reliable companion since birth. That push shaped your skeleton, calibrated your inner ear, and trained every muscle in your body to operate under a constant downward load. Humans built civilizations on the assumption that the push would never stop, never change, never require explanation. And the inquiry has peeled back 4 layers of certainty about that push, one after another, and found that every layer conceals a deeper puzzle. And the reach extends beyond gravity into the structure of physics itself. If one fundamental force turns out to be emergent, an illusion generated by deeper processes, then a follow-up puzzle arises at once. Electromagnetism, the strong nuclear force, the weak nuclear force, could each be a macroscopic shadow cast by some microscopic underpinning that nobody has seen. The original paper does not answer that follow-up. Only gravity is addressed, but the logic of the mathematical result, the demonstration that a familiar effect can emerge from encoded states without any fundamental field, opens a door that cannot be easily closed. Physicists have a word for the situation the analysis has uncovered: underdetermination. The word means, roughly, that the available data is insufficient at present to select a single theory from a set of competing alternatives. 3 spatial accounts of gravity match every experiment. An informational account, built on completely different foundations, also matches every experiment. Explanations keep multiplying. The number of experiments that can distinguish those explanations remains 0. The original question that opened this thread no longer has a simple answer. Is gravity really space-time curvature? Maybe. Or maybe the question itself assumes a version in which gravity is a property of space-time that turns out to be one arbitrary choice among several equally valid choices, none of which can claim exclusive truth. Or perhaps the question itself is poorly formed, the way asking what color is the number 7 is poorly formed. If gravity is emergent, asking whether gravity is really curvature is like asking whether warmth is really kinetic energy. Both formulations conflate 2 levels of rendering that do not occupy the same tier. The philosophical consequences cut deeper than any single equation. The existence of multiple equivalent accounts might mean that none of them captures reality, or the equivalence might mean that all of them capture reality equally, and the human desire for a single correct answer is the illusion. That puzzle has no answer today, and the puzzle might never have an answer. A deeper possibility lurks behind the difficulty. The puzzle might be incoherent rather than hard. Asking whether space-time is really curved might resemble, in kind, asking whether the economy is really inside a bank vault. The economy is a collective effect. The vault is a metaphor that confuses more than the metaphor clarifies. In 2019, Veselin Petkov, a physicist at the Minkowski Institute in Montreal, pressed a related argument from a different angle. If general relativity is taken seriously as a rendering of space-time geometry, Petkov wrote, then falling objects do not resist the fall. Those objects are not being acted upon by any force. The gravitational field in the structural reading is not a force that pushes or pulls. The field is a feature of the geometry. And if the geometry is one of 3 equivalent renderings, the status of that feature becomes even more precarious. Petkov's examination does not invoke entropy or encoded states. The chain of inference stays entirely within the formal tradition. But the conclusion converges with the Amsterdam researchers' conjecture from a completely different direction. What humans call gravity might not qualify as an interaction at all. After 4 chapters of stacked record, the case has arrived at a place where the honest response to the original mystery, finally, is a confession. We do not know what gravity is. Equations are precise. Predictions match observation consistently to more decimal places than most branches of science can dream of achieving. Every experiment confirms the equivalence principle to 1 part in 10 trillion. Every metric account and every informational account produces the same observable universe. But the nature of the effect, the process beneath the calculations, the reason the ground holds, remains genuinely unknown. That vertigo is not a failure of understanding. The vertigo is where gravitational physics actually stands at this moment in history. Consider what that position means. The most familiar sensation in human experience, the one companion that has accompanied every person ever born, from the first breath to the last, rests on a foundation that no physicist alive can identify. Rival formulations describe the sensation with equal precision. A theory whose architect rejected the popular explanation still dominates every classroom on Earth. And the deepest hypothesis on the table says, plainly, that gravity is the universe doing bookkeeping on encoded states, producing a macroscopic result that feels as real as the chair beneath you, but dissolves into pure abstraction at the smallest scales. And the trail has one more obligation before the file can close, because every claim presented so far, the missing force, the competing maps, the architect's rejection, the emergence hypothesis, has been building toward a reckoning that demands an honest answer. How much of this is actually true? What holds up under the harshest scrutiny available? What collapses under examination? And what remains, stubbornly and beautifully, a genuine mystery? That reckoning is next. So how much of this is true? That question deserves a direct answer. After 4 chapters of stacking evidence, after dismantling layers of certainty about the most familiar sensation a person can have, the case owes the viewer an honest reckoning. What survives scrutiny? What collapses under pressure? And where, honestly, does the trail go cold? Let us start by clearing the noise, because the findings in this case have been picked up, distorted, and weaponized by people who were never part of the original inquiry. Search the phrase, "gravity is not real," on any social media platform. Thousands of posts will appear. Most are authored by people who have never opened a physics paper. The claim has become clickbait, a headline engineered to generate outrage rather than understanding. And the clickbait version gets the conclusion backwards. Nothing in this case argued that gravity is fictional. What the case showed is that the mechanism beneath the sensation, the process that produces the downward tug, remains genuinely unresolved. But the tug itself is measurable, repeatable, and as constant as sunrise. Instruments detect the effect with extraordinary accuracy. Every satellite confirms the phenomenon through the precision of the orbital path. Tides arrive on schedule every single day, driven by the same phenomenon that holds your feet to the ground right now. Dismissing that force as not real is not skepticism. That dismissal is ignorance dressed in contrarian clothing, and the distinction between the two matters here more than anywhere else in the case. A second distortion needs the same correction. Every time a documentary or a science article examines a limitation in the standard framework, a wave of headlines announces with breathless confidence that the most celebrated physicist in modern history got the answer wrong. Einstein was wrong. Sells clicks. But that framing misses the point entirely, and the actual record tells a very different story. The field laws from 1915 remain, to this day, among the most precisely verified predictions in the history of measurement. Starlight bends around massive objects exactly as the mathematics demands. Ripples in the fabric of space, picked up by laser interferometers spanning kilometers, match the predicted waveform so closely that even now, the agreement still startles the teams who run the detectors. Orbital precession checks out. Time dilation aboard satellites checks out. Frame dragging, established by orbiting gyroscopes, checks out. Not one failure. Ever. What the earlier chapters uncovered was never a problem with the accuracy of those equations. Rather, the disagreement concerned which physical picture, which geometric language the calculations actually describe. The math is solid. What the math means remains contested. And a third misconception needs to be addressed head-on. Rival spatial renderings do not mean the framework is broken, unstable, or in crisis. This is worth emphasizing. Equivalent formulations of the same mathematics are common across every branch of physics. Take 2 examples. Lagrangian mechanics and Hamiltonian mechanics describe identical phenomena using different mathematical languages. Schrödinger's wave equation and Heisenberg's matrix formulation deliver identical quantum predictions through entirely distinct formalisms. Having 3 spatial accounts that generate the same field laws is unusual in degree because 3 options exceed the typical pair. But the pattern is not unprecedented, and the equivalence, rather than undermining confidence, actually reinforces the robustness of the underlying physics. Three separate roads arriving at a single destination by different routes is stronger evidence for that destination than any one road alone. Now, with the noise cleared, a harder question arrives. If the equations are confirmed and the competing accounts are equivalent, what exactly is the controversy? Ontology. The controversy is about what is real, and the honest answer requires sorting the evidence into tiers with no hedging and no evasion. Here is what has been proven, beyond reasonable dispute, through decades of experimental confirmation. Every object in the field accelerates at an identical rate, regardless of composition, regardless of mass, no matter what the internal structure looks like. Torsion balance measurements at the University of Washington have pushed the precision of that confirmation over years of patient refinement to a level that no other equivalence test in physics can approach. No violation has ever been recorded. Not a single anomaly has ever survived replication. That equality between inertial response and the pull of mass is bedrock, solid, tested, and unshaken. Every formal rendering of the field laws reproduces the full catalog of tested predictions. Whether built on spatial bending, on torsion in a flat arena, or on deformation of measuring instruments in a space that is both flat and torsion-free, the output is the same. Starlight deflection, wave propagation confirmed by laser interferometry, orbital dynamics and frame dragging, cosmological expansion, photon frequency shifts near dense objects. No rendering has ever failed a test, and no rendering has ever produced a result that the others cannot replicate. The bedrock holds, and the contrast with what follows matters because the next two tiers are substantially less certain. Look at what that bedrock means for the viewer personally. The pressure beneath your feet right now is real. The same pull that has been present since the first moment of your life, the companion you never chose and cannot escape, is confirmed by every instrument ever pointed at the problem. Whatever gravity turns out to be at the deepest level, the feeling is not an error. The feeling is an accurate reading of a real phenomenon. The debate concerns the mechanism beneath the sensation, not the measurement of the experience itself. Here is what is possible but unconfirmed. The entropic conjecture proposes that the downward tug emerges from changes in encoded microscopic states rather than from any geometric property. A derivation built on statistical principles rather than spatial structure reproduces the same field laws. That derivation is internally consistent, with no identified logical gap between postulates and conclusion. And the objections that have been raised, the dissipation concern, the absence of a named substrate, the worry about smuggled geometric assumptions, remain unresolved in both directions. Critics have not delivered a killing blow. Proponents have not delivered a confirming signal. The conjecture sits in a narrow strip between dismissal and acceptance. Quality of the reasoning holds the proposal in place. Meanwhile, the absence of a decisive measurement, one clean result from one well-designed experiment, keeps the proposal from advancing further. Quantum corrections offer another avenue. Classical actions of the competing models diverge at the quantum level. Extra quantities that separate the classical renderings, quantities that cancel in ordinary calculations, no longer cancel once. Quantum effects enter the picture. Cosmological data, drawn from supernovae, baryon acoustic oscillations, and cosmic chronometers, have been tested against quantum-corrected versions of both the standard model and the torsion-based approach. Both remain consistent with current observations. Neither has been excluded. Future surveys, conducted by next-generation telescopes and lower-frequency gravitational wave observatories, may push the measurements into territory where the quantum-corrected results finally diverge. But that split has not arrived. For now, and possibly for decades more, the window remains open. And here is what is genuinely unknown, perhaps unknowable. Whether the spatial fabric of the universe is actually bent, or actually flat with torsion, or actually flat with deforming rulers, may be a question that experimental physics simply cannot answer. At the classical level, the competing accounts differ only by surplus quantities in the mathematical action. Those quantities do not affect the laws of motion, and the quantities do not alter any prediction that a telescope, a detector, or a satellite can record. If the gap between the candidates is permanently confined to those surplus terms, then asking which candidate is real may not qualify as a scientific question at all. Philosophers working at major research universities have spent years examining that possibility. One position holds that the underdetermination is genuine. Perfectly equivalent readings, by definition, prove that no single geometric picture corresponds to physical reality. A competing position disagrees. Future theoretical advances, perhaps a completed quantum theory of the gravitational field, will break the tie and select a unique formulation. A third position, more radical than either, suggests that the demand for a single correct reading reflects a human bias, not a feature of nature. All three accounts might be equally real. Or, put differently, the universe might not prefer a single language for describing how mass and energy shape the motion of objects. Specialists who study that problem professionally have reached no consensus. The debate is sharp, rigorous, and far from settled. Now for the verdict. Delivered with the intellectual honesty the case demands, the verdict is layered. The downward pull is real. Mathematical machinery describing the effect has been tested across decades to a precision that few branches of science can approach. Between inertial response and gravitational response, the tested symmetry is the most precisely verified in all of experimental science. Those facts are settled. Preference for bending over the alternatives is a product of chronology, not evidence. The standard account arrived first, became embedded in the curriculum, and was never dislodged because no measurement could provide a reason to switch. That historical accident does not diminish the validity of the standard framework. Every calculation performed in the bending framework remains correct. Every prediction remains confirmed. But the accident removes any claim that bending holds a privileged position among the options. Convention is not the same as truth. The emergence conjecture, after more than a decade of scrutiny, is neither confirmed nor eliminated. Reasoning behind the proposal is sound, and the implications are genuinely profound, but the substrate remains unnamed. No laboratory has ever detected the microscopic degrees of freedom that the model requires. No instrument has measured the encoded states that, in the entropic picture, generate the macroscopic sensation of weight. Honest assessment places the conjecture in the category of worth taking seriously, not established. The proposal might be a genuine breakthrough waiting patiently for confirmation. Or the proposal might be a beautiful mathematical coincidence, one that collapses under the first experimental probe. Both outcomes remain on the table. And the deepest question of all, whether any single geometric vocabulary captures a physical truth about the universe, or whether all three are human languages imposed on a reality that does not speak any of them, remains genuinely open. That is the reckoning, honest, layered, and deliberately incomplete, because the science itself is incomplete. Some of the evidence is bulletproof, some is suggestive, and some of the puzzles might outlive everyone watching. A century of research has delivered astonishing precision and genuine confusion in equal measure. The equations have never been wrong, but the equations have never explained by themselves what gravity actually is. But the file cannot close without one more entry. A pair of physicists found a crack in the wall that separates the three descriptions, a crack so narrow that most of the field has not noticed, and so deep that the fissure might reach all the way to an answer. Sebastian Bahamonde, a theoretical physicist splitting time between the University of Tartu in Estonia and University College London, had been studying the mathematical links between the competing formulations for years. Bahamonde understood a detail that most popular treatments of the debate overlook entirely. Classical actions of the three formulations differ by surface terms. Those surface terms vanish from the classical laws of motion, which is why no classical observation can distinguish the options. But surface terms do not vanish from every physical context. One context in particular amplifies surface contributions rather than erasing them: the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed very close together in a vacuum would experience a tiny attractive force. No charge, no magnetism, and no obvious reason for any pull. But quantum field theory demands that even empty space is not truly empty. Virtual particles flicker in and out of existence constantly. Between two closely spaced plates, the wavelengths of those virtual fluctuations are restricted. Only wavelengths that fit between the plates can exist in the gap. Outside the plates, no such restriction applies. That imbalance creates a net pressure, pushing the plates toward each other. The force is minuscule, but repeated measurements, performed with increasing precision since the late 1990s, have established that the force is real. Here is the crucial link. The Casimir effect is a surface effect. Physical consequences arise because the plates impose constraints on the quantum vacuum. Those contributions are not abstract bookkeeping entries buried in a Lagrangian, far from negligible. When physical plates are present, the contributions produce real, measurable forces that laboratory instruments can detect and confirm. Now connect the pieces. The three versions of gravity differ by those same terms. The Casimir effect is driven by plate constraints. A gravity-driven version of the Casimir effect, if one could be engineered and measured, would produce different results depending on which version of the field laws is correct. The three candidates would yield three distinct Casimir energies tied to the field. And for the first time in the history of this debate, the riddle, which description captures reality, would, at last, become a matter that a lab instrument can settle. Bahamonde, working with Mir Faisal at the University of Lethbridge in Canada, published the argument in a prize-winning essay for the Gravity Research Foundation in 2019. The proposal relies on a specific physical system, superconducting plates. Ordinary metal plates do not work for this purpose. In a normal conductor, the lattice of ions and the surrounding electrons respond to passing disturbances by moving together, tracing the same geodesic path. No differential motion occurs. The gravitational coupling to the plate is, by a wide margin, too weak to measure with any current detector. But superconductors change the picture entirely. Below the critical temperature, electrons form Cooper pairs, bound quantum states that exhibit a property called non-localizability. Cooper pairs do not follow geodesic paths the way normal matter does. Quantum binding forces the paired electrons onto trajectories, diverging from the paths traced by the ionic lattice. That divergence produces what the research literature calls enhanced mass conductivity, a measurable current of mass driven by the differential response of the paired electrons and the lattice to passing field disturbances. Enhanced mass conductivity means that superconducting plates can reflect field radiation in the microwave regime through what the literature labels the Heisenberg-Coulomb effect. Reflective plates, in the gravitational context, supply precisely the conditions required to produce the same plate gap effect in the field of gravity. The proposal is concrete. Place two superconducting aluminum nanostrings in close proximity. Cool the system below the transition temperature. Then use an optomechanical cavity readout designed for extreme sensitivity to measure differences in the Casimir pressure between the two strings. Because the surplus quantities in the three actions differ, the predicted quantum pressures also differ. Measuring which energy the system actually produces would select for the first time a single description as the physically correct one. And the numbers are not science fiction. Richard Norton and Simon Groblacher, who contributed to the feasibility argument, showed that nanostring platforms, paired with optomechanical readouts, can detect pressure differences down to 6 millipascals. The predicted signal from the Casimir effect between superconductors, driven by the field, exceeds that threshold. Bahamonde and Faisal noted in the original essay that even if a more refined calculation reduced the predicted magnitude by 10 full orders of magnitude, the signal would still land within the detection range of existing hardware. Parallelism requirements for the superconducting elements, often the hardest engineering hurdle in plate gap measurements, have already been achieved in resonator platforms built for superconducting circuit research. The tools exist, the detection threshold has been met, and the theoretical work connecting those extra terms to measurable quantum pressures is peer-reviewed and published. As of today, no team has performed the measurement, no results have been announced, the proposal sits in the literature, prize-winning and peer-reviewed, waiting for a group willing to build the apparatus and record the signal. And the implication reaches further than the apparatus. For a century, the puzzle of whether the spatial fabric bends, twists, or stretches has been treated as a philosophical curiosity, beautiful but untestable. Conference panels debated the matter. Journal articles explored the matter from every angle, and the answer was always the same. The puzzle cannot be settled because no experiment can distinguish the options. The Bahamonde Faisal proposal transforms that status entirely. For the first time, what was philosophy becomes engineering. Build the plates, cool the apparatus down to superconducting temperature, record the output, and for the first time in the history of this science, the universe might answer in a language that does not require interpretation. The case began with a simple observation. A person who stops resisting the downward pull feels nothing at all. That silence opened the first crack. Rival descriptions widened the fracture. An architect walking away from the standard teaching deepened the gap further. The emergence conjecture dissolved the flaw entirely. And now, a proposed measurement using quantum plate conditions between cooled metallic strings might, for the first time, put the flaw back together, or confirm that the flaw was never solid to begin with. This case started with a feeling that everyone has known. The trail ends with a measurement that nobody has made and everyone should want. The next chapter of this case has not been written. And for the first time in 100 years, the instruments to write that chapter already exist. The ground holds. The mystery remains. And the inquiry, at long last, has a path toward an answer. You are sitting somewhere right now, and a pressure is pushing you down. The same pressure that opened this case. The same companion that has been there since birth, pressing against your feet, pulling at your organs, holding you against a surface you never chose. You felt that pressure at the beginning of this investigation. You feel the pressure now, but the pressure has changed. A falling person felt nothing, and that silence exposed a crack in 3 centuries of physics. 3 geometric languages describe the same territory, and nobody could tell the maps apart. The architect who painted the most famous map walked away from the building, and the world never noticed the departure. A string theorist in Amsterdam proposed that the sensation is a performance, staged by encoded states that no instrument has measured. Every layer of certainty about the most familiar experience in human life dissolved under scrutiny, and the thread connecting each layer is the same. Familiarity was hiding something enormous. Gravity is not a force. The equivalence principle, confirmed to 1 part in 10 trillion, proves that much. A falling person and a floating person are identical by every measurement ever devised, and no experiment has produced a single exception. That finding is settled. But whether gravity is curvature, torsion, non-metricity, or something emergent from information written on surfaces nobody has seen, that question remains genuinely open. The geometric descriptions work. Every prediction matches observation. The experience of weight is real and measurable and constant. And the deeper nature of that experience, the mechanism beneath the sensation, is one of the most honest mysteries in physics. We do not know what holds you down. That confession is not a failure of the science. That confession is the science delivered without pretense at the frontier where equations end and genuine puzzles begin. This investigation was never really about which equation describes gravity most accurately. The investigation was about the distance between familiarity and understanding. You have felt the downward pull every second of every day and never once questioned the feeling. The most familiar experiences in a human life are often the least understood, and recognizing that gap, truly recognizing the gap, is where wonder begins. You are standing on solid ground. Beneath your feet, the earth. Beneath the earth, a question that no physicist alive can answer. The ground holds. The mystery remains. The real question was never which equation describes gravity best. The observations keep pointing toward a reality far stranger than any single framework can capture. 3 centuries of certainty dissolved under scrutiny, and the replacement is not a neater answer. The replacement is a deeper, more honest mystery, one that physicists are still mapping at the frontier where equations end. If you learned something new today, hitting the like button really helps. The algorithm uses that signal to show this video to other viewers who might enjoy the material as well. I will catch you in the next one. Let curiosity guide you. Keep learning and know that you are always appreciated.